Okay, so during the last lecture we've been working on our during the last exercises we have been working on our linked list, and there was some homework. So I think for now this project is mostly complete, since we cannot really do much on it, since most interesting things are already a homework assignment. So today we will start with another container type, which is also quite a useful helper. And a new item, table h, and this will be a so-called hash table. So the containers which we have been using until now, they all have the property that they you can put something in, you can get it out, but if you would like to find something that's stored inside, then you need to go through the whole container and look in the worst case on every single element before you find what you were looking for as the last entry that you looked at. That happens. And of course this is quite inefficient, especially if you program some things where you have things referring other things, and then you might very easily find yourself in a situation where if you just slightly increase your data set, your computational um, resources will be twice as many required, or even worse. So you can easily, using such simple linear containers, find yourself in situations where the complexity of your task grows exponentially with the amount of data that you are handling, which is quite unfortunate, because if you're doing some simple tests with a small data set, then the system might behave okay and fast enough. But as soon as you want to use it for something productive, then the system gets impossibly slow. And to solve such issues in this small subsection of computing, when you have container types, you need containers which allow you to do fast lookups, meaning lookups where you can where you first of all you are storing the data in such containers with a defined key. So you have a value, a portion of the value defined as being the key by which the data are to be looked up, and then the containers are structured such that such a lookup can be very, very fast. So you don't need to go through the whole list and compare every single entry, but using different tricks you can reduce this to either the order of log n, or even have a constant lookup time. So there are generally two types of commonly used data structures to enable this fast lookup functionality. One is a binary tree, so it's a sorted sort of container, and there the lookup times are order log of n. So if you double your data size, so let's say you had 100 elements and then you double to 200 elements, then the amount of comparisons on average that you need to do to find what you were looking for is only increased by one comparison. So it scales quite favorably. However, such binary trees are a bit complicated to maintain, because for them to work correctly, they need to be properly balanced, and this is complicated. So there is another data structure which can be used to achieve a similar goal, a so-called hash table, which we will be implementing today. And the idea with such a hash table is that from the key value you generate some so the key value can be anything. It can be a whole string, it can be just a single number. It really is quite flexible, and from this you are generating a short hash value, which you are using in the truncated form as a index in an array. So ideally no matter how large your array is, how many entries you have, you generate a index from the key, and then you just look up in this place of the array, and ideally you expect to find what you are looking for right there and then. Of course, in reality, with realistic values, you will get collisions, so that you will have multiple keys that for the given size of the array give you the same index. In which case, this is simply solved by being able to store multiple entries in under each array index, and then if your hash values don't perfectly distribute amongst the available array size, then you will get a small amount of linear lookups to check in one of the array places, so-called buckets, if that's the first entry there, or maybe it's the second or third entry there. But normally, if your hash function is behaving correctly, you should have maybe one or two lookup comparisons per bucket. It should not degenerate to a situation where most of the array is empty and most of the entries are all stored in one bucket. That would be very unfortunate, because then you get, as already mentioned, the very bad behavior of looking up in a linear list. Yeah, and the hash table is much simpler to implement than a binary tree. That's why we picked it. And one thing that needs to be, of course, said as with regard to the performance of these systems, looking up with a table is usually the fastest option. Inserting in a table might sometimes be a bit slower, because you from time to time need to grow the array, which means you need to reshuffle quite a few data. So this is a bit more complicated. But what you can do is you can, for example, allocate larger arrays up front, so that you just invest some memory into better performance. This is a good strategy and works quite well. Yeah. Also, another thing to be said about the tables in comparison to other data structures that we have used is that, for example, with linked lists, what you can do is you can embed the list next and previous pointer into your object, so that you can really reduce memory allocation. This is of course not something you would use in modern code, but in either code for Arduinos, where you really need to save every byte of memory, or all the driver code. This is even in quite a lot of modern Windows driver code. This is quite a common approach, because it's very efficient. You don't need a wrapper object to keep the actual object. And if you have a situation where you have like some sort of custom memory allocation mechanism, then you might also not want to expose it everywhere. And then the whole list implementation can run just by copying pointers around, while other types might require additional memory allocations. In case of a for example, a binary tree, you can do it similarly. You can embed the necessary pointers directly into your object, and then the tree can be constructed and maintained without any additional memory allocations. With the table that we will be implementing today, this is different, because the table, in addition to the elements, needs to have this array. This names is giving hash table basically, and this array needs to be allocated separately. And as already mentioned, it might be reallocated on an as-needed basis. So you always have some additional memory allocations, and you need to expose the memory allocator to your code. Of course, in normal user mode applications, this is not really relevant. You could then just use malloc or new or whatever, and it works fine. But if you are doing some low-level stuff, you might not have a memory allocator available everywhere. Okay, so let's start. So the thingy will of course be called class C. How do we call it? The array was called C array, then we just call it C table, and we will want this to be a template. okay, for key. So we have two types, like the array. We only had one because we only had the type, but here we have the actual keep, and then we have the value type. Type, and what is usually necessary with this hash table is to have some mechanism that allows you to define a custom hash function. So you would not want to have only one hard-coded hash function and that's it, because then you wouldn't be able to use many different types. You would be limited to only use those types for which the hash function has been implemented, and this might either be insufficient, or if you have data which in some particular way don't play well with the hash function, as already mentioned, the table might degenerate to more or less as a single list, which would be very unfortunate. So it's always good to test your hash function implementation, and if it doesn't behave as expected, then provide your own. So here we will have a third argument, h, which will be a hasher to generate the hash values from our from whatever we feed to our table. Okay, so we of course will need something to keep the entries. In principle, one could of course try to minimize here also the memory usage to embed, to use the key basically directly from as a defined field from our type, and then add the necessary pointers into it directly. But since this is of course not elegant and it doesn't allow you to use any types but only types which have been properly prepared, we will, like in our other implementations, create an object to contain here the data. And with regard to memory allocation, it's not that unfortunate, because we can make just an object with embeds k and type, so we can allocate everything in one go, which should be fast enough. Struct as entry. And as entry contains unsent int hash, so it contains the hash value, and we will see why this is quite a good performance improvement to have this value kept pre-computed. Then it will contain, like a linked list, a pointer to the next entry in the bucket. So as entry p next is equals null. In principle, one could also implement this as a doubly linked list for very exotic applications, but normal hash tables don't give you any particularly fancy means of working with them. So unless you want the table to be able to be traversed in both directions, then you don't need a previous a pointer, and the next pointer is just good enough. In principle, we could of course kind of take our list now here and use it as since it's already implemented, but it's more efficient to do this a second time. Then we have of course our key, which is needed as the hash values might not be necessarily unique, and v value, which actually contains the value. And then of course the second object we need is our internal data type. So like with array, we want here to have an own internal pointer, so that we can abstract a few things away, and if needed also easily implement a copy and write mechanism like we did with the array here. So again, this is something that of course would not be possible implementation wise if we would be constrained to not having a memory allocator available, but we have, so we use it. Plus we want our container types to all follow more or less the same architectural designs, and copy and write is quite a convenient mechanism. Okay, and this thing will have a size t account. This is just a convenience feature. We just want to know how much data is contained inside our um, array, our table, so that when we um, printing some debug information, we don't need to count all the entries, we just look up and then we know. Then we will have another count, which will be the bucket count. Basically, it is the size of the hash table, which of course might not be the same and often will not be the same as count. Whether it will be the same or not will depend on our grow policy. So there are approaches where you would want to have always as many buckets as you have entries, but of course this means that you always only grow by one, which is very inefficient. You would rather want to grow like by always double the size of the table and then wait until it runs full without any further allocations. And of course when you remove elements, you ideally would not want to shrink your table. Now if you know that we might have a use case where the table grows very large and then gets small and then stays small for a long period of time, then you might want to implement also some mechanism to shrink the table back again. This is something usually not necessary, although if you are implementing a table as a generic container type for some framework, since it is supposed to be very generic, then you would also implement some shrinking mechanism, simply because it's you don't know what your user will do and you don't want your user to change your implementation, so you must create your implementation in a universal way such that this will satisfy all the needed use cases and not just be somehow inconvenient for certain users. Okay, so let's continue. Right, and of course the most important thing is our actual hash table. So we just here make a pointer buckets, and this contains our hash table. So link. Now we added a constructor and destructor. Destructor just calls clear. We add a clear to our array. Where we use release, we could also use release. Then let's stick with this naming scheme. Okay, good. So of course the most important thing is something to be able to insert something, so we will start with an insert function. And since here we have keys, like for an array, an insert always inserts. For a table or also a binary tree, basically for data types where you have keys, the behavior of insert might be different depending on what you want. So when you're inserting something with a key and then you insert something with the same key, then you have a conflict, and how you resolve the conflict depends on depending on how you want to use your container type will depend on how you want the conflict to be resolved. One option is to return an error and don't insert it. Another option is to overwrite the current entry with the new entry. And the third option is just to add and then have two entries with the same key inside of your data structure, which is doable. It's for table, it's easy. For the binary tree as well, but it might be of course it complicates a few convenience features. So with the array, did we edit this? Yeah. So with the array, we have this square bracket operator, which takes an index and allows us to retrieve an element at a given index. And for tables as well as for binary trees, it's kind of convenient to have a square bracket operator which just takes the key as argument instead of an index and then returns you the value at that key. And this of course fails if you have multiple values with the same key. There are other problems of course with this approach, since this operator is always assumed to return a valid entry. means that it is not just a retrieve functionality, but it also implements an insert. So if you try to square bracket get something with a given key, if it doesn't exist in a table, it will be created. This is why you should have also a proper function to access something, one which either gives you a pointer, which then can be null if it doesn't exist, or one which or another function which allows you to test does it contain something, and then you can use the square bracket operator, which of course is kind of inefficient. So what you could also do is you could configure your table or your tree such that if you try to retrieve something with the square bracket operator which does not exist, that then it will throw an exception, and then you have to catch this exception. But since exception handling is generally very slow, so this is not really a recommended approach. It's much more efficient to just have a proper function which allows you to get something but not insert it if it doesn't exist, in which case it will just give you a null pointer, and then you just check the return value whether it's a null pointer. So given that we have these different behaviors, it might be useful to be able to either have multiple insert functions like insert unique, insert replace, etc., etc. Or what we can also do is we can add a parameter to our insert function which will allow us to define the insert function's behavior. And I think this is the most convenient approach, so let's do it. Enum insert mode normal 0. This will be replace on duplicate. Then we will add multi, that will be 1, which is just it inserts it inserts just multiple entries. And then last one that we will want is no replace 2 comma return an error when a key is already enlisted. So this covers mostly all the different use cases that we might have. We could add some additional flags in case if we would have a doubly linked list and we would want to traverse it in both directions or something like that, but for now we don't need that. So our insert function will will have a return value. If it fails to insert, then it returns false. Fans k key value const value, and our int mode is equals normal. Good. So that will be our insert function, and it can be quite convenient because basically we will just check if the thing is enlisted, and then we make a decision what we do. So of course we will need to have some helper functions for that. One will be something to find an entry, so as an entry asterisk find pointer const key finds key, and then of course we will also have a insert function. Let's call it I mean we could call it without no, we need some name. Let's say just let's call it insert value, and it takes key and value, and it always inserts. So it doesn't care that an element with this value already exists. So our logic here will be quite simple. We use our find to check if this thing already exists. Entry find key, and if it doesn't exist, then entry will be null. But if it exists, so if it exists, then we make a decision. If mode and no replace, then we return false. Yeah. We should improve this. We can check if this is not multi, so does and multi is not. Okay, so if we would have allowed for multiple insertions, then we would not enter in this if at all. So here we already know it's either no replace or override. And if it is override, then we just, since we already have the entry, we just replace the value with our current value, and then we are already done. I don't show. And of course, if we haven't found something, we need to insert it. So insert value, key value, and we return true as well. Okay, so now let's take a look to our two functions. We'll of course start with the insert function, since it's more interesting. So the insert function knows that it wants to insert something, so it can already start by creating a new entry. So the insert will never bug out because it already found something existing. All those use cases have been covered here at the top already. So we create, and we just use new because it's convenient. So we create our entry, and then we want to compute our hash value. Why is this IntelliSense not working? I call this type. Let's change this to V. I always use V everywhere. IntelliSense still doesn't work. Well, then let's continue without IntelliSense. Just one look struct table that looks all correct. We can include it somewhere that it actually processes the file. That might help. But I don't think this will fix anything. Yeah, well, then let's continue manually. Hash is equals, and now we first should think about how this hashing mechanism will work. Since here we are providing a type and not a function pointer, but a type, so how this would be implemented, and we would generally just create some object struct, let's call it int hasher, which will just hash int values. You could also call it like default hash or something, and then make it handle different types. That would also be an option. Why not? Default hasher. We just give it a lot of static functions. Static on int hash int key. Return something like this. And then we'll of course need to do more hash functions. So if this is passed here as the age, then we can here access it by age double point default hash, and then we pass the key to that, and this will give us our hash value. Of course, we will need for more complicated types, of course, so a bit more complicated hash functions, but these hash functions don't need to be like real cryptographic hash functions, which take forever to compute and are collision safe and all of these nice features. It just needs to somewhat randomly distribute the input values into our output parameter space. It doesn't need to be particularly sophisticated. It just should not be terribly bad. So we can, for example, for a int, do something as simple as just XORing it with a 01010101 bit pattern. This will already be good enough for most applications if you only have integer values that you are feeding to that thing. Okay, let's continue. So of course the next thing will be to set our key and value. We can maybe improve this slightly. Let's call it insert. This will be a pointer, because we might have situations where we don't, where we want to insert like an empty element and we don't necessarily want to create something, then copy it, and so on and so on. Although that is not really an improvement. Yeah, doesn't matter. Let's just leave it as is. We can change it later if we find this to be more useful the other way around. Okay. Okay. So now we have our entry. Now we need to put it into the table, but we have not created the table. So we will need to create it, and we will do it by implementing a resize function that will basically be made such that it either creates a new table if none exists, or it resizes the table, which also means it creates a new one, but then it just shuffles the data around. Something is complaining here for some reason. I'm not sure. We probably have some stupid typo somewhere. Let's maybe shortcut this. In the end, I think we just return the entry, and this one, let's just return it null. And try to build it to now it doesn't complain. So it was only complaining because we were not returning a value. Okay, then we don't need to continue with that. We can continue with our implementation work. So if no m, so basically m is null, or m bucket count is less than m count divided by 2 plus 1. So if any of these conditions is true, we need to resize the table, or we want to resize the table. Size t u new size is equals or new count actually. Is equals m question mark m bucket count. We just grow it by a factor of 2. Then 2 or 10. So if there is no table, we start with just 10 entries, and if there already is some table, we always just double its size. And then resize table to new count. So now we need, of course, our new count, and then what we also need is some insert entry function, which just inserts our entry. So this shall never fail, so we just give it no return value. Oops. And in principle, so in practice, this will never fail, but what might fail is this resize. So if we run out of memory, then this would fail, but at this level of failiness, this could also fail. So if we want to implement the whole thing in a fail-safe way, whenever we allocate memory, we should test whether memory actually was allocated or if it wasn't, in which case we then should bug out somehow. Simplest way is just to throw some own exception, which might not be great, but it terminates the program in a deterministic way, which is already okay. And such an exception would indicate that it was because of an allocation failure, so we would know that we don't need to search for some bigger issues, but just first of all check why it ran out of memory. So it already pinpoints the potential problem quite directly. Okay, so resize. We'll make it void, but as said, this is not ideal. Size t, new count. And first of all, we need to create a new m. So s table new m is equals, and for this we will could create a create function, but I think we can just do it instantly. So we used the new before, so let's stick with using new. Do we want to stick with using new? No, we don't want. We want to use malloc. We want to use malloc because what we want to do is here, that's like an empty array, but we want this to be not 0, meaning if we just take size of this thingy, it will always just go to 0 here, and new uses size of. So what we want to do is we will this needs to be a pointer. We will use malloc, and malloc we can Caesar of size of this, and then plus whatever else we want. Caesar of entry times bucket count, new count. So this will create us an object which basically here has the 0 replaced with something bigger, and gives us in one allocation our two helper variables plus the array, instead of having like one object just containing a pointer to an array and then a second allocation for the array. So this is quite an efficient approach. So we create this thingy, then we need to of course initialize it. U count is 0, bucket count will be new count, and we should 0 everything else. Memset how do we call it? Let's just call it buckets. It's not strictly a pointer, it's an array. Buckets, comma, 0, comma, wait, that's not right, that's really a pointer, and now it's correct. Okay, so we just memset everything, and we have our new m, and it's filled with 0, so this is a good starting point. So what we now need to do is to extract all the data from the existing m, if an m already existed. So and since we have a hash table, since we have a linear singly linked list, this is quite easy. Let's be consistent, PDR. So we will just collapse the thing into one large list, but only if m exists. So if m exists, then for size t is like m u bucket count, dash I minus man semicolon. Okay, so this will iterate through all our values, always giving us will that always work? Wait. Yeah, that will work. That will work fine. So the way this works is we get here, we start with the count, which is not a valid index. It's one too many. Then we enter here. We take away 1. So e becomes a valid index, the highest index in the first iteration. But since we use I minus minus instead of minus minus I, what this condition sees is the value before it was minus minus. So if we then arrive here for the last go through, we see with when I is 1, we I minus minus, so we get the first index 0. The thing here still sees 1 and allows us to do it, and in the next go through we enter here with a 1, sorry, with a 0. We make minus minus, so we get like u int max, but we don't care because the condition sees the 0 and breaks the loop before we enter here with a very invalid index. Okay, so here we are. Hence entry is equals buckets von I, and while pantry is not oops, why is this, while this is not null ptr, next is equals entry next entry next is equals head is equals entry is equals next, and repeat it until we are done. And once we are done, we will set a bucket count to 0. We will use this as a optimization later on inside our release function, and then we can release whatever we had. Where's our release here? Also, release is not yet implemented. Right, so we set this to 0, we release, which also means, oops, we need to create this void release function. We also had to do. Right, so at this point m is no longer valid, or it never was valid. M is equals m new m. Yeah, m is equals new m. And now we just need to put everything from our list, which we pulled out of the previous table, into our new table. So we just use another loop. So per head, while this is not 0, we will need another insert function. We already have an insert entry, we don't need another. Perfect. So we just copy something again. Right, so we started with head. So instead of entry, we go here with head and insert entry. Head. And this brings us to our next function, our insert entry. Okay, I don't think we forgot anything. So let's continue. So here we want to find the index. And this will be our entry. The entries already have the hash values pre-computed. So you see here, we would need to recompute every hash value if we wouldn't have it cached, but since we cache it, then this is super efficient. We have our hash, but of course this needs to be in a value range from 0 to bucket count -1, and we can do this very easily with a modular operation with the bucket count. Of course, this is like a division, so it's very inefficient computation-wise. So one might want to improve on this. We could, if we would have if we would constrain the size of our table, we could work here with bit shifts and or with just bit masking. But this, as said, doesn't allow us to have an arbitrary size of the table. It always needs to be a power of 2, which is not wrong. But for now, let's just stick to doing it simpler. Though I might add here an optimization. Let's make this 8. And we can actually add a function that would give us the valid index, so that if we want to improve this later on, we can do it in one place. So mk index int hash. So we just put it into a function. Yeah. Make index, and we will reuse this somewhere else. And once we want to optimize this, we can. Okay, so we have our index. So then we look up a bucket as entry. Then reference bucket is equals buckets from index, and we have our bucket. It might be something, or it might be nothing, but we don't care. We just insert at the top. So entry path next is equals bucket, and bucket is equals p entry, and of course u count plus plus to indicate that we have more entries inside of our table. And that's that. Well, other things of course are missing. So let's test it. Let's try it out. So go to the bottom. C table. Let's say for the key, let's take int. For the value, let's take something complicated, or not. Let's take our string. We don't need to use something else. Let's use our own string. And for the hasher, we said we already have a hashing function. Though we could provide this here as a default argument, then we don't need to specify it each time. Okay, so my table punct insert wait, like something. Oh, that's a bug. It should be a comma. I think that's what broke our IntelliSense before. Right, so this should be fixed. Suck my table, punct insert, let's say 1, 2, 3, and value string could actually use our C string A because we have a definition for that. Actually, that should cast from a string on its own, so this would actually already work. Just let's see if it compiles. Yeah, it did, and it didn't crash. So let's 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. And now we want to use find, which we did not implement yet. Table. And we could either expose our find pointer or create a or call it make a wrapper function called get or something. Yeah, let's just expose our find. I think this is the most convenient approach. Find pointer. Or we just call it find. Let's just expose it. Okay, so the find is quite simple. We just need to look up whether the thing exists. So whether it's whether an entry for it even exists, and if it exists, then check the keys, because as said, the keys may change tone null pointer. So if there is no m, of course there cannot be anything. We grab our index. We could already do this. So we we need the hash. Unsigned int hash is equals hash key. Make index from hash. Get our bucket from index, and while let's call it entry. That is inconsistent. Let's call it here, but here we already have entry. Okay, then let's stick to entry. Let's leave it as is. Right, when this is not LPTR, then we check if entry now intelligence works hash is equals hash. This is a very cheap comparison. It's just one operation, one instruction, maybe two if yeah, it will be like more two, because we need to load both from memory. But on the other hand, the comparison operation can like have a address as an argument, and the value of hash can be cached in the register. So if the compiler optimizes this pretty efficiently, it is just one instruction for the comparison, and then a jump, and then a conditional jump. So it's really efficient. But of course, just the hash being the same doesn't necessarily means that the value is the same. So we also need to compare the key. So if the hash is the same, then we compare key. And if you attended lecture part 1 last year, you know that this comparison will never be executed if hash already failed. So we only do a expensive comparison of the key when we are already reasonably certain that it probably will be true. Might not be, of course, but assuming our hash function works well, the chances are pretty good that this will end up true. Okay, so we have our key comparison, and then if that was fine, then we just return our entry. Okay, this can be made more compact, but of course, if it is not true, then entry is equals entry per next, and we continue. And if we go through the whole thing and don't find a match, then we and then we just return null. Um, right, so let's use it. My table. Right, so we have our string a pointer paste is equals my table. So if you look in for um, already implemented hash tables, you will not find one which just gives you a naked pointer to the value. You will either find ones like in Qt, which where the find value function just gives you a copy, so we cannot modify what is contained. If you want modify, you need to use the square bracket operator. Or if you are using the STL template, the standard template library, you can of course use also there the square bracket operator, but you can use a find function which gives you an iterator which allows you to change the value, but it's a bit more inconvenient. So this get find pointer function we have here is a very nice thing. So let's look up. Oops. Let's search for this. And why is this? Oh wait. It cannot be find pointer. We need, because find pointer gives us like the internal object. We don't want that. We need to, let's call it find value. This of course needs to be here. The return type is wrong. We need to return a v find value. Entry question mark entry value, and we want to reference, or yeah, now it's fine. Okay, let's put a breakpoint somewhere here and see if it works. String. Yep. So our lookup table works. So now we need to look into some assignments that we can assign you as a homework. So first of course, when we insert things, we'd like also to remove things. That sounds useful. So here, int remove const k reference key and pool. Technically that also might be an int remove key and value. So usually when you are removing things from such a container, you just want to remove something by key, and this is in most cases good enough. Of course, if we have multiple entries with the same key, then you want to remove all of them usually. So this remove function will return the count of the elements that it has removed. So for example, if you remove something that is not in the list, you will get 0, and this might be an information you want to have, might be useful. But of course, if you are inserting things into a list, like multiple things with the same key, then you might only want to remove a specific one where the value matches your matches the value that you have given to it. Of course, in case of STL, you would just use an iterator, find the thing, and then just check it manually. But we want this here to be convenient, so we have the second remove function, which matches not only the key but also the value. So both must match, and then they will be removed. And given that in principle you could insert the same thing with the same value and the same key twice, we will here also count how many have been removed instead of just returning true or false on success or failure, because I said the success might also be more than one element. So this will be the homework. They 0, 8, 0, 1, 2, 0, 2, 0, 2, 6. To do. Matching key and value from the table. Okay, so in principle both are quite easy to implement. You don't need to modify the table itself. You just, like in our find pointer, are actually maybe you could, like in our find pointer, you just get the hash, get the index, and then you only modify the one linked list. So if you have implemented the remove function, isn't there a remove function of a linked list? Oh, we forgot to add this. Implement append, prepend to iterator. Really? That's unfortunate. That will be yeah, then I guess this will be another homework. Really, this is unfortunate. Remove is very important. Press and begin and find arrays. Although we have arrays, okay? We have arrays. That is kind of, that is in principle good enough. This is good enough because, like, if you remove and then you wouldn't want necessarily something where you have to provide the actual value. I think with the list it's fine. We leave the list as is. But basically you can see how this works here in this arrays. Did we implement this anywhere? Yeah. Table. So here this will just then work the same way. So it's quite easy to remove something from a list. I'm just thinking whether we want to still have a second assignment to make the list doubly linked, but I think this, do we want this? It would be nice in a way. We could then iterate for it in both directions. Let's add this as an additional assignment, and particularly because you already had this here in list, so it's not very difficult. You're basically just using the knowledge that you gained doing the list assignment now to just do something else. Homework from the implement below functions. Homework, so let's 1, 2. Previous. this will be like buckets will be head, and then we also need a tail value. So no, wait, we don't. This always points to the top, and the other one will also need to point to the end. Yeah, so we need bucket bucket heads, bucket tails. That doesn't work nicely. That's annoying. That is annoying because then we cannot make this like a single location implementation. How do we do that? There is a complicated way to do it. Implement every bucket as a sort of ring buffer. So basically the last entry will point back to the first entry, but then you cannot like run around in it. I think this complicates things too much. Let's just leave it out. This complicates things too much. I'll just stick to this. Yeah. Okay, any questions? Okay. So if there are no questions, then we should find you something you can do during the lecture already today. We will need a volunteer to implement a void dump table function. We will need to make this, however, a bit smart. So void stern k print key const k reference key comma value. Okay, and the usage is as simple as it gets. Dump table. Zack. Key. Zack. Zack value. Zack. And of course this is then int, and this is string a. So here just printf %i, comma e, and here is printf %s, comma not e, key value punct string semicolon. So we just need to provide, of course, the print functions because we might contain anything. And the assignment for which we need a volunteer now is to just print the table. So we obviously start with a printf table dump \n, and then you should just the function should just iterate through all the buckets, and inside each bucket through all the individual entries, and then just print key double point value, key double point value, key double point value, like new line each time then. And when we are done let's print f. Oops, that wasn't typing. Just something to indicate that we are done with the list. So, any volunteers? No one? Okay, then let's see who I have to pick. Mm, 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 mm. Maybe Mr. Ali Usman.
Yes, sir.
Do you want to try to implement the table dump function?
Okay, sir.
Then you
Sir, could you share me?
one moment, please. I think the IP changed in the meantime. So I will write it to the chat. The IP is this, and the port was, I think, 6. I think this was the right configuration. If it asks for a password, then it was correct. If it doesn't, then I'll just in parallel look up whether that's the right port. Hmm. Yeah, the port is right. So when you try to connect with VNC Viewer, it should ask for a password. Is it working? Hmm.
Sir, I'm finding. Sir, this is not working. I don't know why.
Um, Let me try.
No such host is known.
That should not happen. Wait. Mm. That is unexpected. That should work. Testing it right now. Just a second. So for me it works fine. Try entering the values again into VNC Viewer.
Okay.
If it says host not found, it probably suggests that you have like some space maybe added or something, and it thinks it's a host name, but it's just an
Maybe.
IP address, so it should be definitely working.
So what is password?
I'll write it in the chat. Where's the chat? Either this or this.
Yeah, it's working.
Very good.
Okay. So I have to make a remove all entries with match key and value for the table.
You have to basically you need two loops. One outer loop which goes from 0 to m arrow u bucket count, and then an inner loop which will for each bucket iterate through all of the bucket entries. How such a loop works, you can look up for example the find pointer example, because there we also are going like through the loop, and just that we are breaking at some point. Here you would just go through the whole thing, and you will use the provided print key and print. Oops, one moment, please. The second one should be print value. And print value functions to print the key and value from the list.
First we use for loop.
First, you create a for loop starting from I0 and then checking whether I is less than m arrow bucket count, and you increment the I by 1 in the last loop.
So which one I have to
So
create, like remove, find value, or dump table?
dump
Uh,
table.
Okay, okay.
Find value is already fully implemented, and remove will be homework. Dump table is for now.
Or we have to create a loop, for loop,
Um,
like this,
First of all,
and
create it in line 88, not at the top,
okay,
and you write for and then round bracket, and then you provide three statements separated with semicolons, one for the initialization, one for the condition, and one for the increment. So the first statement will be the initialization. So you just define a variable called I and assign to it the value 0, since we want to start with the first entry in our array.
like this,
No, you
or
want to assign it, not to compare anything.
oh, sorry, 0, like this.
Almost. The variable will complain that it's undefined. It needs a type. You need to write size t before I. So size underscore t space I.
T, sir, T.
Size
Okay,
underscore t
size underscore and
t
side underscore and T.
and now space.
Yeah.
Okay, now after the 0 you put a semicolon, and then you write the condition. You want I to be always less than our bucket count.
Like I see, I implemented 2 0, and then what we have, right, sir?
You want now a condition which says that the variable I should be less than m arrow u bucket count.
I less than.
Yeah, the other one. Now it's greater than. You want less,
Okay, sir. Okay, sorry. I less than
and then you write m arrow bucket count, m arrow u bucket count.
M and sorry, sir. I'm not understanding.
Arrow, like the minus greater than. Like in line 80, you have entry arrow, and here you want to have m arrow. Yes,
Like this.
and it already suggests you a u bucket count.
Yeah, yeah, U bucket. This.
Click. Okay. Now you can write another semicolon, and the third statement in the for loop will be executed after the loop finished. Not after it finished, after the loop body has finished on each iteration once. So here you enter, for example, an increment like I plus plus, so that each time the loop body finishes, the I gets incremented before the comparison will be executed.
Okay. Then after that, what we have to add, sir?
I plus plus.
Okay. We- Plus, plus. And then semicolon after that.
And the next step will be inside the loop. You need to inside the loop you need to create a second loop, a while loop. But let's think how we can simplify this since we are running out of time. You can take a look into. You can basically copy this whole thing. But you should, of course, to the for loop give it a body. So use curly brackets. So after your for loop in line 89,
Sorry, I copy this like
you also need line 105. hmm And here, before you paste it, make or after you paste it, the thing you pasted must be um, surrounded by curly brackets. So after the for, yeah, here.
yeah.
Yeah, and if you reapply the last curly brackets, it should format everything nicely. If you delete the brackets in line 90, 87, no, sorry, in line 9,
97.
if you delete the bracket in line 98 and then re-add it, retype it, then the thing will format the whole body. Now type it again. Yeah. Okay, so almost done. But instead of index in line 90, you need, of course, our I, because we are counting I through.
At which place, sir? Starting.
90, replace index with I. Wait, and I see there is a might be a bug
Uh, index.
with I.
I.
Um, may I have the mouse for a second? We have a
No, no, index. I know.
small mistake here and here. Okay, now it's fine. Right. So now you can delete the content of our while loop except for the last line. So lines 93, 4, and 5 can go.
Sir, repeat again.
You can delete line 93, 94, and 95.
93, 94, and 95.
Mm-hmm. Yeah. And instead of those three lines, you just now can print the content of the current entry.
With C out.
You can print it using print key and print value to print the individual values, and then you should use printf to print a double point space between them, and after them to print a \n so that we get a new line.
Printf. And, what I have to, sir, print.
Just write add a new line before 93.
Sorry, like this.
Yeah, and now in this line you write print key, open round brackets. Yeah, but with the right capital letters, like it's suggesting it. And open curly bracket, open round brackets. And now write p entry, as it suggests. Entry, not entry, not pi, but pi. Wait,
PI.
P P E, not PI but PE.
Oh, sir. Okay, sir.
P
P
entry.
entry. Yeah, this one.
Then arrow,
Arrow right.
not comma, arrow. The arrow operator. Minus greater than. You already used that.
Okay, sir. That's great.
Key. Now you
This.
close the brackets. Semicolon.
Yeah. Yeah.
Okay, now in printf, you add quotation marks, two quotation marks.
Sir, I have write it in next line.
In the next line, add quotation mark, double point space quotation mark, like the double quotation marks, the shift 2 on the German keyboard.
Sir, here.
Double quotation mark
In 93, line 93.
in 95 now.
Here, like this.
Nope.
Am I right, sir?
The double quotation mark, that's an @ sign, that's not the right character. Yeah, look in line 102. You want the same thing, just you want instead of plus plus, have a double point space.
No, sir. Okay, okay, sir.
Double point space.
And what I have to print, sir?
Double point and then a space.
Double. Mm. Or like please write here. I am not understanding.
Double point, like just a dot and a dot on top of the previous dot. A character which is made up of two dots.
Like this and
No,
space.
on top of each other, like one character. I think it's just shift dot if you have a German keyboard. If you have an English one, I'm not. Like in line 86 before the backslash n. Ah, yeah, you found it. Now a space. Now again a quotation mark.
And like uh,
Nope,
this.
quotation mark now. The one you already had before the double dot.
Notation. Sir, I'm not getting what's quotation.
Quotation mark, like you had before after printf bracket. You already had a quotation mark,
Yeah, yeah, yeah.
and then you
Okay.
just now need to put again. And now you close the bracket and semicolon. And now next line. Basically, you can just copy the two lines you already had. Yeah.
These two.
Print key and printf both without the bracket. Yeah. And paste it after the printf. And replace print key with print value. And of course key with value. The V needs to be capitalized. Okay, and in the printf in line 89, replace the content of the quotation marks with a backslash n.
Here. 89.
In line 98, sorry.
Oh, sorry. 98.
Here replace the double point space with a backslash n.
Where in this place
Yeah,
in starting?
inside the quotation marks, replace
Yeah,
the content. Instead of double dot space, we want a backslash n. Just delete the two characters inside the quotation marks and replace them with a backslash n.
like this.
Yeah, just remove the double dot in the space.
Double quotation
No, the
replace.
quotation must remain
Oh,
in the space.
yes, space.
No,
Okay.
the space needs to be removed. Both. Now I have two spaces. Okay, and now you can press the play button to see if it works. Wait. Let me have the mouse for a second. Okay, first of all, that is not quite right. Index. This. Okay, and it printed the table correctly. Okay, that worked. And we are over time, so it's time to finish. So I'll stop the recording.